Hello, this is Jim Doyle with Donaldson Company, Clean Fuel and Lubricant Solutions Group. Welcome to the webinar, Critical Information and Concepts for Applying Clean Solutions to Achieve Bulk Lube Cleanliness. The objectives for the presentation today are to go over typical OEM cleanliness target specifications for different types of lubricants, go over a system design for best practices, go over and review what information is required to implement best practices in lubricant handling, and then finally assessing fluid cleanliness properly to ensure that everything is working as it should be. First, we'll go over OEM target cleanliness levels for different types of fluids and lubricant applications. For hydraulic, gear, and engine oils, OEM recommended cleanliness levels start out for cylinders, hydraulic cylinders at roughly an ISO code of 2018-15. We'll get into a little bit more detail on what an ISO code is, but that's a shorthand term for the cleanliness level of the fluid. The pumps that would run that cylinder and any other hydraulic circuit, however, need to be at an ISO cleanliness level of ISO 18, 16, 13. And a little higher pressure and more sensitive components include axial piston pumps and fixed piston pumps. An ISO code of 16, 14, 11 is common for those, as well as with transmissions, and that's pretty common cleanliness. Servo valves are probably the most sensitive component in hydraulic systems and control systems, and they have an ISO cleanliness requirement of 15, 13, 10. And then just for reference, diesel fuel high pressure common rail fuel systems have the highest level of cleanliness requirement. They run at the highest pressure with the tightest tolerances and need an ISO cleanliness level of 1296, a very, very, very clean state of fluid. Generally, what to remember is the tighter the tolerances and the higher the pressure the system is running, the tighter the filtration that's required to get to that cleanliness and maintain it either in bulk or in the system to make sure things run properly without getting wear due to particulate entrained in the fluid. So is your hydraulic or gear or engine oil clean enough? I mentioned that the ISO cleanliness code, or ISO 16889 is the actual standard, is a measurement of contamination in the fluid, and that's really the term to describe the concentration and distribution of particulate in a fluid. It's a shorthand code describing 4 micron and larger particulate, 6 micron and larger particulate, and 14 micron and larger particulate. Visually, it's pretty easy to tell the difference between these samples. These are 100x magnification microscope images of cleanliness levels. This is an ISO 222118, so too dirty for any system. And how this is prepared is a known volume of fluid is put through a filtration patch, and you look at, count, and size the particles to come up with an estimate of the concentration and distribution of dirt in the fluid. So here's a 2018-16, as we mentioned. A cylinder can operate and tolerate a fluid like this because they don't have any really tight tolerances. But typical cleanliness for gear oils, gearboxes, and engine oil, that kind of thing, is an 18, 16, 13. You can see there's less and less particulates in the view here, sort of how much pepperoni is on the pizza. If you're looking at it here, there's less and less toppings on the pizza as you go along here. Higher pressure components in hydraulic circuits and transmissions have a typical standard of ISO 16, 14, 11. You can see there's very few particles left there to count in the viewfinder as you look around at the debris that was in a known volume of fluid. And 1296, you can see almost no particulate. There's virtually nothing there other than the patch and the grid line visible there, the green grid line. Fuel now needs to be very, very clean for high pressure common rail fuel systems, but the transmission circuits and other components also need a certain cleanliness to maintain trouble-free operation. Next, I'd like to go over system design best practices to give you an idea of what a typical system looks like before and as filtration. Consider this a general lube tank in your lube room, or a trailer with tanks in it, or maybe even a lube truck. You have a truck that delivers oil into that tank. Typically oil is offloaded at maybe 40 gallons a minute, but for larger tanks it can come off at a little higher flow rate. That's usually a positive displacement pump pumping oil into the tank there. And you'll have a high pressure stick pump, as they're sort of loosely referred to, high pressure pump that pumps out to the hose reel at much lower flow rate but at very high pressure. You can see pressures of 300 to 1,000 psi are typical for those type of dispensers. You also may have a system pumping at a higher flow rate, say to load out of a bulk tank into a mobile lube delivery truck or something, or trailer, and that'll run an air-operated diaphragm pump that runs at much lower pressure but higher flow rate to fill totes and other tanks and things like that. So this is a pretty standard system that generically we would encounter, and then we're looking to improve lube cleanliness and maintain it clean as it's being dispensed into equipment. So the place to do the most work is on the inlet side, cleaning the fluid before it goes into an already clean bulk tank on site. And you would say run a manifold of filters here to handle the flow rate on and clean the fluid to the specification you're looking to for that fluid as it's offloaded off the truck when you take possession of that fluid. So you clean it first and protect it in storage with a trap breather, and perhaps, since you're going to have compressed air to run one of the dispenser side pumps anyway, purge the headspace of that tank to prevent any condensation. Purge it with dry air, and that'll prevent any condensation from building up in the top of that headspace, and then that runs down and reacts with additive package in the oil and tends to drop solids. That maintains that tank clean and dry. As that new oil comes in, it stays there clean and dry. And then you're protecting it in storage there from particulate contamination, as I said, water. And then polishing it on the outlet side with a high pressure filter on a high pressure pump that can handle pressure in service up to 1,000 psi, or on a higher flow dispense application with a lower pressure pump. You can do that with the larger blue spin-ons that can handle that flow rate. And that's the polish side of things. Those filters should last a very long time. If you've already pre-cleaned the fluid coming in and maintained it clean and dry in storage, there should be nothing to plug those filters on the outlet unless something happens. So there's sort of an insurance policy. So what information is required for lubricant sizing? If you've watched any of the other webinars we've done on fuel, we've got that down to just a couple of questions that need answering, and you're able to get going on things pretty easily. For these lube systems, because of the different types of pumps and viscosity, there's a lot more information. So first off, the pumps in the system may be some sort of positive displacement pump coming off of the truck. It's probably not going to be driven by an electric motor there, but there may be a transfer pump on site. But that's going to be a positive displacement pump that probably has a relief valve in it to prevent very high pressure. Even though that pump can push it, the pump will just begin to slip and offload flow rate will drop. But the truck either is equipped with that, or there's a full-time stationary pump there for offloading that fluid into your storage tank. You want to know the pressure range that it runs and the flow rate. You'll need to know that for sizing things there. Next is the type of pumps on the outlet side of the tank, and if they're air-operated piston pumps and they have a ability to produce higher pressure, they'll run basically a multiplier from, say, 3 to 1 to 10 to 1 of the inlet air. And say you have 100 pounds of air pressure in your shop air, that'll generate 300 to 1,000 psi with that pump. The higher the ratio of the pump, the lower the flow rate it can produce. So the low ratio, the 3 to 1, can produce about 12 or 13 gallons a minute, and a 10 to 1 pump can only produce a few gallons a minute of flow, but it can generate a lot more pressure. One very important thing to note with these types of pumps is they're on a hose reel when the nozzle is off, when you're not dispensing fluid, the pump builds up until it deadheads to the highest pressure that it can generate. So they shut off at maximum pressure, and this leaves that hose reel sitting there at between 300 and 1,000 psi when it's not in service. When you're actually dispensing fluid, the pressure in the system is much lower and flow is happening. When flow stops, if you've ever been to a oil change place, you can hear when they stop pumping oil into your car, the clunking of that pump slows down until it stops, and that means it's deadheaded at maximum pressure until someone pulls the trigger again. The other type of pump I had mentioned for higher flow transfers, typically out of a tank into totes and things like that, is an air-operated diaphragm pump. That is a 1-to-1 ratio style pump. It only generates whatever pressure the shop air is. So 100 pounds of pressure air can generate 100 pounds of pressure in the line. It doesn't have an ability to multiply, but they can flow at much higher flow rates. 20 to 80, maybe even 100 gallons a minute are not uncommon with these pumps. Therefore moving larger volumes of fluid and not pump dispensing necessarily into equipment, but more into other tanks. But these pumps also shut off at maximum air pressure, and they can create a situation that I'd like to mention here. This is a very serious aspect of these styles of pumps that shut off at maximum pressure. If you've ever picked up, I want to talk about something called thermal expansion. If you have ever picked up a garden hose that has been sitting in the sun with the water shut off and noticed that it has a lot of pressure in it, that pressure did not come from the pressure in the water line. It came from heating of that garden hose in the sun. That's called thermal expansion. And that water wants to expand, and it's being constricted by the hose. And you pull the trigger and it squirts some water and the pressure drops away to nothing. That goes on in these systems as well, and the high pressure hoses that these systems are built with constrict and hold that pressure very well. They can increase pressure, hundreds and thousands of pounds of pressure in these systems if the oil begins changing temperature significantly. So for every 1 degree Fahrenheit the oil in that hose increases, it generates another 43.7 pounds of pressure. So 10 degree Fahrenheit increase in temperature in that line, and you've got 437 pounds of pressure build up above the shutoff temperature. So consider a lube tank that's sitting down at ground level in a shop, or maybe even outside the shop, and the pipe comes in the building, goes up across the ceiling, and then down to a hose reel. That tank that's sitting down low is probably quite a bit cooler than the piping that runs up across the ceiling in the shop. If it's a heated shop in the winter, that can get much warmer up there, and you can increase an awful lot of pressure. The manufacturers of these pumps have gone from a warning to a mandatory requirement to install thermal expansion pressure relief systems on these pumps. If they start seeing pressure above the shutoff pressure, they open up a valve and bleed it back into the tank, and you really want to make sure that's there, because the hose reel can burst, the nozzle trigger can burst, or even the filters can burst. It's overpressurizing the system well beyond what it's supposed to for use in these. The next most important thing directly for sizing filtration is also temperature. I'd like to walk through a quick example here of a typical hydraulic fluid, an ISO 46 hydraulic fluid. I'm sure you've heard it described as an ISO 46 hydraulic fluid. What defines it as that is its viscosity at 104 degrees Fahrenheit or 40 degrees Celsius. You can see it has a viscosity of 46 centistokes. That's nice thin hydraulic fluid. It pumps very easily at that viscosity, and it's even thinner when it's actually in service and working. However, at room temperature, that same fluid has a viscosity significantly higher than that. It has a viscosity of 135 centistokes. So it's now gotten about 4 times more difficult to pump or push through a filter. And if it gets even colder, say it's a tank of ISO 46 hydraulic fluid outside in the northern half of North America in the winter and it's cold, it could be up to 1500 centistokes. It's many times harder to pump at 1500 centistokes or push through a filter. So just a rule of thumb to remember for oils, for every 18 degrees Fahrenheit decrease in temperature, the viscosity of the oil and the pressure drop across a filter doubles. So this is a very significant issue in sizing ambient condition oil. To see what happens with that information on a single filter, We'll look at our ISO 46 oil here again and say the lube room is maintained at a minimum of 50 degrees Fahrenheit. So your oil is 50 degrees Fahrenheit. That's fine. That's a decent number to consider. And that oil has a viscosity of 264 centistokes, just a little bit over this 250 curve I just circled here on the chart. And that is the pressure drop through a single light oil filter at 250 centistokes. And looking at what the pressure drop across that filter is in comparison to that viscosity, we can comfortably get 12 gallons a minute through that filter and be at about 7 or 8 pounds of pressure drop across the filter at that temperature at 12 gallons a minute. So that's a nice safe zone to size. We usually try to size 7 to 10 pounds of pressure drop on a clean filter. Now, if we see that fluid drops to 14 degrees Fahrenheit and back to 1500 centistokes, you'll see the 1500 centistoke curve here, or almost vertical line as you'll see it. And I can only get 2 gallons a minute of flow at the same pressure drop through that filter. So if I was to try and get 12 gallons a minute of flow rate out of that filter at 1500 centistokes, the pressure drop would be well over 100 psi across the filter. That's not acceptable. You're just not pumping efficiently and filtering efficiently there. So that actual temperature you're filtering oil at is very, very critical. For outdoor tanks, it's good to use the average January temperature. So if you go on any weather website and look up for that location what their average winter temperature is, high and low, and pick the midpoint of that. If it's an outdoor tank, that's a decent estimate for that minimum temperature you need to size for. If it's inside a shop somewhere or something and it's a heated lube room, you have a better idea of what the temperature is. But temperature is critical to figuring this out. Again, we'll look at this chart, and I want to go over one more aspect of this. As far as picking the filtration. So for, say, the inlet side filtration, and I have 250 centistoke oil and I can get 12 gallons a minute per filter through there, and my truck's going to offload at 40 gallons a minute. I can use 4 filters in parallel. The P561880 manifold, the smallest 4-filter manifold over there, will handle that 40 gallons a minute without any trouble. If we are filtering at cold oil at 1500 centistokes, I'm going to need 20 filters in parallel. So 2 of the 10 filter manifolds, the P568933 manifold, bolted in parallel to get 20 filters in parallel and handle that. That's how much difference the temperature makes in selecting the right size manifold for ambient conditioner oil filtration. In operation on equipment, most oils are in a viscosity range where you can't really mess up picking a filter and going with a tighter filter and not having an issue. In this in bulk and ambient condition filtration, actual temperature and its viscosity of that fluid is critical. It's not uncommon for people wanting to over-filter the fluid and say, well, I want to get it a little bit cleaner just because that's what I want to do and it's the right thing to do. Well, consider again our 250 centistoke and 1500 centistoke behavior of the previous filter. This is the next tighter filter in the product line that fits on these heads. And here is your 250 centistoke pressure drop curve. And you're back down at the same temperature at 50 degrees Fahrenheit. You're back down to 2 gallons a minute per filter. If you want to use the next tighter filter, you're again going to have 20 filters in parallel to handle that flow rate. So you go from sizing it correctly, having to put only 4 filters in parallel, to having to put 20 filters in parallel to have the same pressure drop. It gets very expensive to overfilter at cold conditions, ambient and cold conditions. So just a word of advice there. Then the lube types and what type of filtration they actually require. Again, I mentioned overfiltering gets very expensive. So for hydraulic fluids, ISO 32 to 46 and 68 hydraulic fluids, we recommend 7 micron filtration at delivery and 8 micron at dispense. That's the bulk HP, the high pressure filter, or 7 micron on a low pressure dispense application. Hydraulic and transmission fluids, those are combination fluids, same level of filtration required there to protect those components. 7 micron at delivery and 8 micron, or the 7 micron if it's low pressure dispense. 10-weight gear oil, depending upon its use, that's not an uncommon, actually not uncommon for that to be being used as a hydraulic or transmission fluid as well. Same level of filtration. When you get to the heavier gear oil, say 30-weight gear oil, it's going to be in a gearbox or something, not in a hydraulic situation. It needs to be maintained at ISO 181613. You only really need to do that 25 micron on delivery, and our most open filter on dispense is a 14 micron on the high pressure side there. Engine and gear oil, again, doesn't need to be over filtered, and it gets very expensive to do. Again, 25 micron on delivery and 14 on the dispense. And the heavy gear oils, same thing. 220, 320, 460, and 680 gear oils. 18, 16, 13 is all they're trying to hit, and you do the same level of filtration there. So it's pretty straightforward. If it's hydraulic and transmission, it's 7 micron. If it's engine and gear oil, it's 25 micron kind of thing. And then it's important to consider the volume of each fluid used over time. That's important because there's new dirt coming in each load of fluid, and you want to make sure you're sized if it's a very high volume oil user. As an example, a mine site will use many times more fuel than they do oil, but a manufacturing plant where they're building mining equipment will use a ton of oil and very little fuel. So you kind of just need to get an idea to size for capacity based on the volume of fluid you're just to give a refresher on what the whole philosophy of clean, protect, polish looks like for lubricants. You're doing a high level of filtration on a fairly thick fluid at the point you take possession of it, so you're offloading it through 4 to 10 or 12 filters maybe. This is a 12 filter manifold. As it goes into your storage tank, you're protecting it there with a breather and possibly purging air over that headspace to prevent condensation and water buildup in the system. And then you're filtering with high pressure bulk HP on the high pressure hose reels, or possibly low pressure one-to-one air operated diaphragm dispenser systems with the higher capacity, lower pressure drop filters that can handle the higher flow right there on those low pressure hose reels. So for every particular site, but just to give you an idea. So again, the required info for sizing a system, the summary of that would be temperature of the oils when filtered. What is it delivered at as a minimum temperature, and what is it stored in your tank at? The types of oil and the delivery flow rate, what flow rate is coming off that truck, and the volume of fluid used over time. Storage tank volume and temperature, again, temperature very important. The pump type and air pressure and flow rates for the dispensing system. So you need to know the ratio of those air pumps on the other side and what kind of air pressure they're running it at. Usually they max out at about 100 to 125 psi for air pressure. And finally, again, a little note about assessing lubricant cleanliness. This is very important. Relying only on machine particle counts for samples sent out to labs for mobile equipment fluids, hydraulic and transmission, and engine and gear oils, can lead you down a very confusing path. You'll start hearing things or seeing things like the filter is not getting the oil clean. We want to put tighter filters in for the application. The stuff is just not getting clean. Again, I showed you why that's a challenge. We have sand in our oil, which seems like a confusing statement that I'll cover in a second. We are not meeting our cleanliness cleanliness specifications. The filters are plugging because I've put really tight filters on, but my oil is not getting clean. The filters are not compatible. It's over what's going on. And what's happening with these systems, here's a standard oil analysis report for a hydraulic fluid or a gear oil. Is it looks like there's sand in the oil as could be a comment coming back to you, and they're referring to the fact that in the contaminant section there's silicon, and everyone assumes that's sand. And silicon can be sand, but it is now an additive in virtually all of those oils, and it's an additive that can really mess up the particle counter. You'll see there's no wear metals or multi-source metals or anything in this fluid, but the ISO count post filter is a 222115. That's extremely dirty. Remember how dirty those images were? That's the dirtiest image I showed you. What's going on there is something called machine particle counter interference. there's an additive in the oil that confuses the counter and makes it believe that the fluid is very dirty. So an undiluted machine count of 23, 21, 16 is, if it visually was 23, 21, 16 is what you would see there on the left. And after doing some sample prep or a visual count, we find that the fluid is actually very clean. It's meeting its 16, 13, 11 target quite nicely. And the machine, if we did what's called a dilution, it seemed to be able to overcome some of that interference and give a representative number. But that's not always the case. What's causing the issue is it's something called silicone anti-foam additive, and it's in most of the fluids now to limit aeration and allow air and bubbles to escape more quickly. And what it is a suspension in the fluid of small spheres that are a silicone material, and they look like particles to the particle counter. They're not there to do damage. They're part of the additive package in the oil, but they can overwhelm the counter and cause it to give high numbers over and over and over, making people believe that the system is not filtering the debris out. There's a study done on this about 10 years ago by the Milwaukee School of Engineering, but it really didn't provide the context that of this conversation, that this fact that it raises the particle count on the particle counter would confuse people into believing that filters are not working and they need to overfilter and keep filtering and keep filtering. So this is a very confusing thing for these applications. You'll put filtration in and people will think it's not working. By far the most direct way to assess it is to do a visual count of the sample. If that's how dirty it is coming in, did you get to the cleanliness targets you need of 18, 16, 13, or 16, 14, 11, or if it were fuel, even 12, 9, 6. Visually, you can tell if it's working properly, and then further look into the machine particle counter interference. But this confuses most people on the mobile fluids for hydraulic and gear applications these days. This is a very tricky thing to work out. Visually confirming the particulate is the most direct way to figure it out. And that's it. If you have any questions, you can contact us at MyCleanDiesel, and if you're not connected, please do connect with us there. Thank you very much.